we have plenty of pizza, right? I think we got plenty of pizza, so feel free to come down and grab a slice or two. Yeah, I guess let's go ahead. Did you start it, Davide?
Yes.
Okay, great. So welcome, everyone. Thanks a lot for coming. There has, one of the themes I think we'll just touch on today is the fact that machine learning has really taken off and been thriving within the last 3 to 5 years. And this attendance, I think, is evidence of that. There's a lot of people across many, many different domains of research at Vanderbilt and elsewhere who have become interested in machine learning. So traditionally, it was more of a computer sciencey tool, but it has migrated out of computer science into lots of different domains like biomedical informatics and many, many others. So the way we're going to do this is we're going to have a panel discussion. So be thinking of some just excellent questions to grill these panelists with. We also have a Slack team. So if you're a member of our Slack team, you can actually go in and ask the questions through Slack. But you can also raise your hand and ask the question that way. I'll have like 3 or 4 questions to kind of start us off with the panelists. But then I'll let you guys take your best shot. So to start us off, David Schluter, am I saying that right? David Schluter is a PhD student in biostatistics, and he's just going to give us a really brief 5-minute introduction to machine learning. Thanks.
So I want to, first of all, thank you, Will, for asking me to give this presentation and to be on the panel. First off, I should note that the original title of this presentation was an irresponsibly brief introduction to machine learning. It turns out, as we're going to talk about no doubt with the panel, machine learning is this sort of broad, nebulous concept that has taken a life of its own in the recent years. And so I'm just going to take 5 minutes to sort of try and get a little bit of a framework around what people typically think of when they say the words machine learning, because of course it's a buzzword. So the first sort of conception of what machine learning is you can go back to 1959, so it says 2000 down there, but actually this first quote comes from a paper that was designed by this guy Samuel to develop an algorithm for automatic checkers playing. And essentially paraphrasing the entire discussion section, he kind of talks about machine learning as being this field of study that allows computers to learn without being explicitly programmed. So, we're in this is pizza and programming, so you can sort of think of a naive program where you define the rules in your checkers game. For example, in a series of if-else statements. So if a player moves this way, I do this way. That is sort of the conception of what he said about what he was talking about when it's explicitly programmed. But of course, that's completely inefficient, and we want computers to be able to learn from their environment with experience. And that takes me to this second quote by Tom Mitchell at Stanford. He defined machine learning as sort of this, he defined this learning task of what computers need to do as a computer program is said to learn from experience E with respect to some class of tasks, T, and performance measure, P, if its performance at tasks in T as measured by P improves with experience E. Okay, so we've got italicized variables here, so we're big league. But essentially all this is saying is pretty intuitive. We want computers to learn with more exposure with respect to some cost function or some, as they say, performance. And so machine learning, like I said, this is a really broad topic, and we're going to discuss different implementations in our respective fields. But machine learning these days is most often associated with the usage of artificial neural networks. So deep learning, recurrent neural networks, the like. But machine learning is actually more broad than that. Typically learning is thought of as unsupervised or supervised learning. And we'll just talk more about what those mean in our respective fields on the panel. And so these are some the nice thing about machine learning is that it's really open source. It's developed by programmers that really are into the philosophy of open source software. And the barrier to entry for machine learning is really low these days. And so these are just some examples of some open source, free to use softwares that are very robust and actively maintained. We got TensorFlow, Keras, Scikit-learn, Torch, and Theano. And those are all they're all free and easy to use, and there's a multitude of examples and whatnot. But I think my 5 minutes are up, so let's get to the panel discussion.
Great. Thanks, Dave.
Yep.
Alrighty. So to start things off, I'd love for each of you to spend a little bit of time introducing yourself, what department you're from, and how you're applying machine learning within each of your respective fields. And I'm going to move my laptop over on top of that table. We were supposed to have a microphone for this event, but it was not brought. So we're going to use the microphone on my laptop for the remote participants. So let's start here.
All right, hi, I'm Yuan Kai. I'm a PhD student in ECS department. So I guess I'm the only one of 2 PhD students here. Right? So but we still have advantage that we are still running code.
It's true.
So basically what I'm working on is the medical image analysis. So traditionally when you see a doctor, right, he asks you to do a CT or MRI, then he have a grayscale image. What he do is he judge, okay, if you have tumor, you have weird organs, whatever, based on the training he got in past 10 years or 20 years. So what we want to do is we want to do the quantitative analysis on those images, which means we want to know what the image is, which organ, where the organ is, etc. And the challenge of the medical image that it typically 3D image, which has millions of pixels in that image, in one 3D image volume. So we want to understand the meaning of each pixel and find the correspondence between the genetic information, between the health record, etc. We connect tons of population. So this is basically how we use machine learning to do the medical image analysis.
Like I said, I'm David. I'm in the Department of Biostatistics. And in my application of machine learning, so I live really in the realm of supervised learning, if you will. I do a lot of regression tasks, specifically survival analysis modeling on EHR records. And in part and parcel with that, I'm working on developing scalable algorithms for Bayesian methods and implementing the current paradigms in Bayesian computing for EHR records.
Great. Hi, everyone. My name is Colin Walsh. I am primarily faculty in the Department of Biomedical Informatics. I also have secondary appointments in the departments of medicine and in psychiatry. So I was a mechanical engineer as an undergrad. I took a brief 10-year sabbatical to go to medical school, residency, chief resident year, and then I moved into informatics fellowship, biomedical informatics fellowship at Columbia University. And it's from there that I actually came to Vanderbilt. I've been here for about 2.5 years at this point, and my work is very much applying machine learning in an applied data science lab. I'm trying to solve problems in the clinical space. 2 quick examples. A lot of the stuff we've been working on in the past couple of years has been in the area of mental health. So for one example, 2 patients come into my clinic, and I'll be going back to clinic in about half an hour, well, I guess 45 minutes. I don't want to leave early. In about 45 minutes, they see in clinic. 2 patients come in, both with depression. I give them both a first-line medication for depression. One does great on it, responds, symptoms are better. The other one doesn't work. We try something else, doesn't work. 5 years down the line, they've tried all sorts of stuff, and we qualify that as something we call treatment resistance. How can we use machine learning with electronic health record data we're collecting every day to figure out who those 2 people are? And is there some genetic signal that we might be able to inform with a clinical phenotype that's derived from the electronic health record? The other big example we've been working on is in the space of suicide risk prediction. A really difficult problem to identify, really hard to screen for, and we don't always do a great job. Can we use data to help shine the light where we should at least be looking to improve our screening rates and trying to prevent an outcome that's really dangerous, which is suicidal behaviors and even worse, death from suicide. So I'll pause there.
My name is Maithili Kunda. I'm an assistant professor in computer science here at Vanderbilt. I've been here about 1.5 years. In our lab, we do research on AI and cognitive science, sort of broadly. And we use machine learning primarily as a tool to study human learning. So for example, how do babies learn to recognize objects? Or how do people learn visuospatial reasoning skills? And it's kind of an interesting scientific question, a methodological question, to think about what can you actually learn. So if you have a machine learning system that learns something from some data, what does that actually tell you about human learning? You know, it's a very high bar to say like, oh, we've modeled human learning here, which we're really far away from still. But what we can do is use these machine learning systems as a way to characterize the structure of the learning problem itself. You know, if we have some representations and algorithms and data, we can say like it is actually sufficient. You know, these are sufficient to learn performance on this task. And so that becomes a way to sort of study, you know, what information are humans getting? Would it be sufficient in our, you know, do we think that this information is sufficient to support this kind of learning? And we also study atypical development in people. So for example, conditions like autism, where we are sort of learning that, you know, one of the things that happens in autism is from really early on, infants are actually getting really different learning inputs because their interactions with the world are different. So those are some of the questions that we ask.
I'm Chris Fonsbeck. I'm an assistant professor in biostatistics. I began as a wildlife biologist. That's what my background is in, and I morphed into a statistician, and then I morphed again into a biostatistician. My focus is, rather than necessarily what we know using machine learning or what we can learn, it's what we don't learn. So I focus more on the uncertainty. So I use a lot of Bayesian methods, like David does. I build software for implementing Bayesian methods, which implement probabilistic models. So we're not interested in just getting a prediction about something, but a confidence, some measure of probability associated with that. I typically am working in the arena of epidemiology and specifically infectious disease. And what we want to do there is be able to make optimal decisions in the face of uncertainty for doing things like controlling disease outbreaks. So if an Ebola outbreak happens in West Africa, what do you do? There are things you know, there are a lot of things you don't know. And we can use machine learning to learn as we make decisions and as we make observations. Using a third branch of machine learning, mentioned supervised and unsupervised learning, reinforcement learning is another way of doing that. So Bayes and reinforcement learning are kind of my two arenas.
Okay, hi, I'm Eugene Paravicek. I'm also in electrical engineering, computer science, department computer science. This is the primary appointment. I have a secondary appointment in biomedical informatics. I do both fundamental and applied research on machine learning. On the fundamental side, you guys are all interested in how to make machine learning work. I'm interested in how to break it. So the field is called adversarial machine learning, and a lot of my research is in that. On the applied side, I use machine learning tools, or my lab uses machine learning tools to do things like predicting human behavior, to predicting incidents of crime or accidents in space and time, using forms of survival modeling, actually, and various other things.
Excellent. Okay. So for these next set of questions, or pretty much for the remainder of the panel discussion, not everyone has to actually answer the question, so I'm just going to kind of let you guys take turns, as you will. So nobody be a ball hog, please. Play nice. But my first question is, what has sparked the growth and interest in machine learning over the past 3 to 5 years? And I'm going to come over here and touch I'm paranoid this is going to fall asleep. So David, could you just like reach over and kind of wiggle it every now and then?
Yep. Who's going to go for that?
So yeah, someone has to jump in.
Was that the question?
So I don't know if these are the only factors, but I would immediately point to the internet and faster computers as two big ones. And I say the internet because I think it has become a clearinghouse for acquiring and putting together large data sets, and even crowdsourcing has been like a huge part of building some of these fundamental data sets that really drove a lot of the progress, in the 2005, 2015 range, I'd say.
Internet's kind of a proxy for the availability of lots of data. And I think that was part of it. These deep learning methods in particular are very data hungry, and one of the reasons neural networks were abandoned for a long time is because they didn't have A, the computing power, and B, the data to feed them. Now we have that.
And one of the after effects of that, and I think David spoke to that well, is the democratization of a lot of the tools that we use. So people who never had access to the types of code to let them build a new algorithm can actually take and apply an algorithm to data they may already have. And then the other thing is we starting to take for granted the fact that this stuff's in our daily life. So the conversation at a very high level is happening in many parts of our life, and at least in healthcare, we tend to be about 10 years behind. So we're finally having that conversation. But those two factors, I think, have been a huge factor, certainly in informatics and healthcare.
Yeah. So kind of along that same vein, can you guys talk about what tools you're using to perform machine learning and whether you're performing sort of models that you've developed yourselves or someone else has helped develop, things like that?
I guess I'll start. We tend to really like scikit, or the Python package for machine learning, but we've used a whole host of things from ours packages for machine learning to Weka to TensorFlow. And we do, as I mentioned, we do a fair bit of foundational work, so we develop algorithms ourselves. So we're actually building a library that's going to be offshoot of scikit.
In my research, I use a lot of the tools that Chris develops, notably PyMC3, and that's a probabilistic programming language where you can specify statistical models in order to quantify uncertainty in your models. So the nice thing about PyMC3 is that it has a Theano backend, and so with a lot of the models that I'm developing, I'd like to apply them to large data sets, and the methods for fitting those models on large data sets often require gradient calculations that are really hard to do by hand. And what deep learning libraries allow us to do, things like TensorFlow and Theano especially, well, part of deep learning requires this idea of backpropagation. And in order to do that, you need to be able to compute gradients on the fly. And so what's nice is PyMC3 leverages that computational backend to make my life a lot easier in terms of the gradient calculation for the models that I'm fitting. So mainly, I would say mainly Theano, but with a probabilistic programming front end.
Yeah, I basically focus on the deep learning side of the machine learning. So basically, I use two softwares. Previously, I used TensorFlow, and in the past half year, I started to use PyTorch, and I realized it's much easier interpretation software and much faster. Not much faster, like 10% faster than the TensorFlow. So now I'm focused on using the PyTorch. And in my research, basically, the first step is to use a state-of-the-art network as a base net, then do my multiplication or add my components or reorganize the network based on this base net. The reason that I need to do that is I want to get my PhD, so I need to introduce my own contribution. Otherwise, if you only want to use it, you can just use the base net.
How big is your data set, and how do you train it and normalize it so you actually, when you're doing like a brain scan, you're actually comparing this part of the brain to that part of the brain? So how do you normalize the images?
Okay, so about the size of the images, it depends on the task. If you are doing something landmark detection, detect some landmarks in the body is easier. Probably you need at least 10,000 of image. If you are doing more complicated, like a brain segmentation, because the brain is complicated, you probably need like 10 times more than that. And to normalize between the training data set, you should first do a registration to make them in the same space. Then it will be easier for your network to learn the brain information, and it's also easier for you to get better results. This is basically my experience.
And how big is your data set? How many?
My answer is as big as possible. As big as possible, yeah. If you have a million, that's good. If you have 10 million, that's better. So.
Is it something you run on the desktop, or is it something you use the network?
Yeah, I both run on my lab computer, because when I develop my algorithm, I use my local computer because it's more efficient. Then I start to ACCRE. Let ACCRE run tons of jobs, something like that.
How big and how long?
The job I'm running today is about 70 hours to train the network.
You said you mentioned you use PyTorch. Are you using GPU implementations?
PyTorch has already done the low-level GPU implementation for you. You only need to define each layer and let it run.
Over here.
So I have kind of a high-level question. Are there key features of a research question that when you hear them, you think, yes, that's a question that we should apply machine learning to? I think one of the things that I'm struggling with is because it's kind of like a hot, sexy thing to do, a lot of people are doing it, and it's not necessarily clear to me which, like, when it's really useful or really appropriate, and when it's just, you know, doing it because maybe you can, but it's not actually going to yield significant insights. Does that make sense?
Prediction is a key word that I look for. So machine learning is one of its best uses is for making predictions. It's not as good for inference. By that I mean kind of learning what causes an outcome. So if you've got lots of data, lots of variables, most of these methods don't do a good job of telling you why it came to a decision that it did or that it made a prediction that it did. But it can usually, with sufficient data, give you a good prediction.
It's a great question. I think also because it's a really shiny hammer right now, and it's easy to walk around looking for those nails. And so you can find a way to turn any clinical problem, for example, in the clinical research space into, well, let me think of a way to throw machine learning at that, which is completely the wrong way to go about it. The use case should determine the methods that apply, of course. So, and I have lots of those conversations where people are like, can't we just use machine learning because it's like the cool thing? That's the implicit suggestion. And often you just like, if the data is not really big enough, if it's not particularly complex, it's a pretty well-specified problem, it's actually probably not the best use of machine learning. It's throwing a really complex tool at something that might be able to specify more simply. And there's downsides to throwing machine learning at everything. One is that it's not just complex in terms of training and expertise and the hardware you need to do that and the data you need to do that, but then actually implementing that is by no means smooth, certainly in healthcare. We don't have that pipeline right now. We're still using, when I go back to clinic and I get a cholesterol panel back, what do we reach for? We reach for a pretty old risk score that gives us some prognostication of a risk of heart attack in the next 10 years, which was built through good old tried true logistic regression. And it's what we got, so we use it, because I don't have that button that just runs Theano on cholesterol panels. So point being, in my lab anyway, its use case comes first. Everything's not a machine learning problem. And then always, if you have a good relationship with the people who have the problem, because we often have sort of a consultant role, and in our research it often ends up being that too, because we partner with people who have the problem. You partner well with them, it's pretty quick that you'll realize, okay, machine learning is not the solution, certainly not the panacea. And often we're the ones who have to kind of talk people down, because it's the kind of thing that's just hot right now.
Yeah, my last question was for Eugene, did you have?
Maybe I don't have a lot to add, but machine learning, as it's commonly known, it's first of all, it's a really broad field, so it's actually hard to answer this question that's really all-encompassing. For example, prediction is something that's very fundamental to things like supervised learning. Sometimes you can use machine learning very successfully to find structure in your data, structure in your data, things like sparsity, whether it's well approximated by something low dimensional. These sorts of things, machine learning tools can be very successful for. So it's hard to answer because there are so many different tools that are really within the field that people call machine learning. And if you brought it into AI, which is nowadays almost viewed as equal to machine learning in AI, there's a whole host of things about making decisions under uncertainty, which are not necessarily even driven by machine learning. They're using other tools. In that sense, I think that it's a case by case. There's not really, in my mind, an easy generic guideline to answer this question. And it's potentially just worth talking it out with people and seeing whether, genuinely one approach is better than another.
Yeah, my last question was sort of related to that, and that was, what are some misconceptions associated with machine learning?
So, for the sake of being controversial, I can say a few things. One thing is that a misconception is deep learning is new. Deep learning is decades old. People have been working on the problem of neural networks for a long, long time. Most of what we consider to be sort of state-of-the-art deep learning is from the late 90s. What makes deep learning really effective and new is what folks on the panel already mentioned, which is lots of data and lots of computing, and the use of GPUs was sort of revolutionary in that sense as well. But deep learning is very far from new. I'd say there's a misconception that people understand machine learning. I don't think anybody understands machine learning, and even people have been doing that for decades. I mean, this is a bit facetious. Of course, there are certain things that are fairly well understood, like linear models are pretty well understood theoretically. Most of machine learning, especially once you go into nonlinear land, the only thing we know is that it works a lot. But beyond that, why it works, why do neural networks work, people don't actually really understand. It just happens to a lot of the times. This is nice because it's nice open opportunity for a lot of people to write papers about deep learning, trying to claim to have understood something we haven't before. It's also very dangerous, okay? And this is something that there's been some discussion in the academic community about, but that's also not well understood. Because you apply deep learning to a particular problem, let's say in the clinical domain, where stakes are high. There's so many things that could go wrong because of the assumptions you inherently make that you don't think about when you apply it, that it should really worry people more perhaps than it does.
So I have one to add. My kind of favorite misconception. So you may have heard me on a soapbox about this before. Just because it's called a neural network doesn't mean that it's doing anything even remotely like what the brain does. And I cannot tell you how many times I read, you read like the latest media article about some group, and it's like they have this system that is now, recognizing cats just like a human does. And it's far from what humans do. For a lot of reasons. And so I kind of think, anytime you see it's just a name. Anytime you see neural network, you should just mentally replace it with like, iterative nonlinear function approximator, and then see if you still believe the claims about, neural possibilities.
Yeah, I can share basically my mistake. I made a mistake before when I run the deep learning networks, this kind of misconception that I had before. So basically when you learn the machine learning textbook, so you typically see two curves, right? One is training curve is like this, and the testing curve like this, and maybe go back means you do it overfitting, right? In the previous textbook, it tell you, okay, if this model has a training curve like this and the testing curve like this, you should probably don't use this network, or don't use this model because it's overfitting. But in the deep learning area, so basically, when I did my internship, I trained two models. One was 2 years ago model, one is the state bar. And I realized the state bar had this kind of overfitting curve. Then I said to my manager, okay, I should use the model 2 years ago. But he said, okay, in the deep learning, the network is super complicated, super non-linear. It basically captures almost all kind of variation you have in your training data. So you can see the training accuracy, the state of our network is better than the previous one. But the reason it's overfitting is that you don't have enough training data. What you should do is not use the old network, is to collect more data and do data augmentation or do some trick to prevent the overfitting rather than use the low-key model. So this is basically the misconception I have.
I have one. I think the biggest one that I see repeated, mentioning what you read in the media, is that now that we have big data, we don't need models anymore. That it's a pretty common one as well. We don't need models. We don't need statistics particularly because we can just use empirical information from our data. But you always have to keep in mind, whenever you get data, big or not, keep in mind, think about where the data comes from and how that data got to be in your hand and what isn't there. One of the features, what big data does is it reduces variance. So the more data you get, the variance goes down. What doesn't go down is the bias. So if you have biased data, more of it is not going to cure that. So you can really run into problems. So it's always important to build a model and know where that model comes from and test your outputs against that model to kind of validate it.
I want to add one more thing. So one of the definitions you had is a classic definition of machine learning where something learns if, according to some metric P, right, it improves with more data. This is again a bit controversial, but I would claim that we don't know an algorithm that actually does that in a provable way for metrics that we care about. And this seems strange, right? So let's take metric as training error. So sort of obviously that's going to be true for most things, but we don't care about training error, right? We care about, let's say, in machine learning and supervised learning, we care about making predictions, which is in some sense fundamentally unverifiable. And you have all kinds of theory, but there's no way to prove that with more training data you actually get better predictions monotonically, right? That's the key. So this again goes into this realm of we don't really understand machine learning. But this one specific example that I think people may have misconceptions about.
I have kind of a more positive misconception, I guess. Right. It has to do with the types of tasks that machine learning can be applied to. A lot of times, we're interested in supervised learning. Like, you essentially teach the algorithm with examples, for example. And that's certainly the world that I live in most of the time. But there are other tasks that machine learning is really good at as well. That, for example, generative models is a kind of a new up-and-coming subset of machine learning algorithms, where essentially you essentially generate data for whatever reason. And one example is in like video games, where it's computationally expensive to perhaps store a particular part of an image or a video frame, and you can actually generate the rest of the frame using these things called generative adversarial networks. And so, machine learning tasks aren't just limited to prediction. Like they're very powerful and able to do all sorts of other tasks as well, unsupervised, supervised, and well, also reinforcement learning is a big thing that people kind of overlook. But Chris can talk more about that if he wants.
All right, questions from the audience?
I have a question. I think that in clinical domains, there are many chances that disease samples are much fewer than the normal samples. It's synthetic data. I wonder what's the usual methods dealing with this? Is it just the oversampling or the undersampling, or is there other approaches that you prefer?
And if you could if someone wouldn't mind restating these questions, so people online can also hear them, that would be helpful.
I'm sorry, I didn't quite catch it. Would you say it one more time?
I can see it, especially in supervised learnings, when your the data set is imbalanced.
Oh, yeah.
How can you deal with this? Especially in clinical domains, the disease, some of the people has the disease are fewer than the normal people, are much fewer. So, what's your preferred approaches to solve this?
Yeah, so the question is basically really in clinical problems is totally true. In clinical problems, it's very often we're in an imbalance, a case imbalance situation. So for example, at least in my work, usually there are very, very rare events that I care about that I'm trying to predict, and many, many, many potential, let's say, controls or those people who I can balance against. Really big problem. Partly a problem where machine learning inherently handles some of that pretty well. However, what people tend to do, and this actually goes back, I think, Chris, you said this really nicely in response to the last question, one of the misconceptions is people will make choices implicitly, and they don't even know that they're sometimes making choices. So for example, I get a lot of papers to review, for example, and the abstract talks about 10 million patients, we built a model, and it turns out they had 100 outcome, and they balanced it against 100 controls that they drew out of that 10 million population. So that's an inherent choice where people said, I'm just going to sample, I'm going to undersample in that situation so that I build a nice balanced case set, I build it, and I've done a great job for those 200 people, but they haven't necessarily done the due diligence to look at the 10 million. So a lot of those choices, I mean, clinically what we try to do is be true to the problem as much as we can. So very often there are attributes of either the cohort or the clinical problem where in fact it's almost enriched just based on the clinical bounds. So it's a clinic setting where it's actually not that many people. Even though you can pull from 2 million, it really only applies to maybe tens of thousands. That's one way. And then the other thing we'll often think to do is to work through some of that sampling. We've done some of those experiments. When I was in fellowship, for example, I was doing prediction in hospital readmissions. So somebody gets admitted to the hospital, And it's very important financially for hospitals around the country to worry about a subset of that population that's going to come back within a certain period of time. There are financial penalties related to that. So for a long time, there was this cottage industry of readmission risk prediction, and machine learning was all about that. So people were throwing machine learning at readmission risk, and one of the issues was we realized clinically, people can't just come back to the hospital. So you can't just say, take all readmissions and bring them back. So we had to make choices around how we define that outcome. So people come back for pneumonia, or they come back because they have chest pain, or they come back for something else. And so we were interested in figuring out, well, can we be a little more specific and actually look for those outcomes instead? Turns out you create a really interesting case imbalance problem there. And we actually did a sub-experiment in one of our papers that came out on this specifically, where we tested the sampling. And we actually compared undersampling and oversampling across a pretty wide bound, and we looked at that performance curve. We essentially looked at our trained test curve doing that. And it turns out what we essentially converged on is that we optimized based on the use case we were in. So we're very interested in the clinical utility of these models. So we optimized based on that clinical problem and basically made a choice around the model, knowing there was a number of other choices that we could have made, but we were very empiric in the way we approached it. And we didn't presume that, well, 20%. We ended up running with 20%, and that's what hit our abstract as basically a 1 to 4 case imbalance ratio. But we undersampled from the data in order to do that. Now, that's a choice. There may be a better way to do it, and I'd actually love to hear from the other panelists on how they've handled it. But that was one clinical example. It's a really, really important problem. Most important thing for people in the audience is to know you're making a choice and be transparent about that. That's the most important thing from my mind.
Yeah, so in general, the kind of imbalance, so I don't have experience with clinical applications per se, but with imbalanced data, I think it also calls for the need to make sure you're using good metrics and good baselines. So imagine you have like an imbalanced classification problem, and like 95% of your data belongs to like one class. You can have a baseline classifier that just says everybody is that majority class, and look, you've got 95% accuracy, which sounds really great, So then I actually see papers like this all the time where they've done something, and then they say, oh, our algorithm is getting 95% accuracy, and it's like, but wait, that's actually just the same as what a baseline sort of classifier would do. And so I think there's a lot of simple solutions to this. I agree that the biggest thing is just to be aware that you're facing this type of issue and handle it appropriately. So for example, instead of just calculating accuracy the usual way, there are lots of not very complicated options for calculating accuracy in a way that accounts for the fact that you have imbalanced categories. And you just have to make sure you're using one of those metrics to provide a better picture of like how accurate is your algorithm actually.
Yeah, so for example, precision versus recall would be a way to look at it. Alternatively, there are various things you can do. Another way you can look at positive, negative class, or one class versus the other, and look at accuracy specifically on each class, and that'll help you tell which is which. But actually, the issue of dealing with imbalanced data, it comes up all the time. Arguably, that's the majority of cases. So there are there are a whole slew of things that people would do in machine learning communities and otherwise. And I don't know literature in that space that well, but I know there is a fairly substantial literature in machine learning on how to deal with imbalanced data.
I just had one thing. There's a publication bias around the area under the receiver operating characteristic curve, or the C statistic. And in case imbalance, depending on how poorly specified the model is, there's the baseline point is very well taken. So if you just give everybody the same prediction, your AUC might be great, but it's based on labeling everybody the same way. You haven't done anything. You haven't predicted anything. And so we tend to not even take those papers if there's no PR curve. If there's no precision recall, it shows that people just aren't even thinking about that. So.
Whereas there's a challenge as far as prioritizing it. So if your readmission prediction is that it really ultimately, if you actually train it, you actually find out this because it either choose up, the go up, not down. We never measure it actually if you do up or down. But if you actually were to measure it, actually you find out because it's actually predictive based on that parameter. And so I think I suppose you choose your parameters carefully, or because I think also your outcomes, like so then knee replacement surgery is a good example where predicting bad readmissions at all costs. Because ultimately the payment model is going to be, no matter what, is the surgeon's fault. Not whether or not they came in for PE or a chest pain, but really just was it readmission.
Yeah. So there's the so one of the other themes here, and I like that point a lot, John. One of the other themes there is also we tend to, especially in the clinical world, we tend to live in a world of convenience sampling, right? It might be convenience sampling on tens of millions of data points from a clinical health record, but it's still a convenience sample. It's what we have. So we take the data we've got and we throw it at problems. And we tend to misspecify, underspecify, sometimes overspecify. So being thoughtful about that, knowing it's never going to be perfect, but the age-old, the George Box quote all the time, right? All models are wrong, but some are useful. We're shooting for the useful.
Someone picking up from there, how important is feature selection and feature engineering that feeds into the models? Because it seems like it's just limitless what you can feed in, different combinations of features.
So maybe I'll start this. This is actually a very sort of deep question nowadays, because there is one misconception about deep neural networks, is that you don't need to do feature engineering anymore. And first of all, your choice about what to measure is an act of feature engineering and feature selection. And in most domains, you get to pick what you measure and what can be layering and so forth. Having said that, if you have enough data, one real power of deep learning seems to be to essentially come up with these nonlinear combinations of underlying features that you can't necessarily think of yourself. And with proper parameterization and sort of controlling for sparsity and regularization and so forth, you can make it so that you can control to some degree for overfitting in theory. And that's true for other machine learning models as well. So so feature selection is always important. The question is really how you do it, and it's model specific.
I would just add the clinical challenge we face is that there's a real craving for interpretability, and that's actually not necessarily where machine learning is strong. So like in suicide risk prediction work, the first question was, well, okay, how did it work? And the second question is, what were the risk factors that were important? And that may or may not be a meaningful question. And we're having a culture change where we're trying to sort of get there. So interpretability in terms of feature engineering is really hard because you don't want to hamper your model performance, but you also, at least for me, a lot of my collaborators are immediately going to want to know, well, how did we get there? And I think we're going to eventually get there because we show that these tools are actually efficacious in practice. We're just not there yet.
If you think you need feature engineering, you're sort of implying that higher order interactions among your variables are important, right? And they're hard to detect and specify a priori. So you get that often in image recognition and image classification, where they're trying to find features associated with circles and different shapes and different colors that would be impossible to specify in a parametric statistical model. Often in some of these clinical settings, we're mostly interested in main effects because A, they're interpretable, but also interactions of more than kind of two-way interactions are hard to interpret and probably aren't there to begin with in any meaningful way. So it really depends on the class of problem that you're addressing with it.
So I have a very applied question. Once you have identified a clinical question, let's say that you think might be well suited to machine learning, what would be the best way to start educating yourself about these methods? Is it playing with some packages? Are there some good Coursera courses? How do we actually get into this space as beginners?
I am going to give a plug to a really good introductory YouTube series by a data scientist named Siraj Raval. It's Sirajrival. And if you can stand like the occasional meme in your YouTube video during the explanation, he has really great hands-on tutorials for all sorts of machine learning tasks, and he has a GitHub that he'll link to the particular task, and he'll even assign the viewers sort of a task to do that week, and then he'll have competitions for them. Like one of the tasks one week was build a neural network to predict on this particular hospital data set, or like the handwriting image data set, stuff like that. So very concrete, understandable examples. He works mostly in TensorFlow, which is great because it's backed by Google. But if you want to look at other sorts of programs that rely on PyTorch or Theano, for example, you might have to look somewhere else. But I think those are really good examples.
Yeah, I wouldn't start with deep learning as your beginning point. Download scikit-learn. We mentioned some scikit-learn. That's a really well battle-tested, very comprehensive machine learning library, very much standard machine learning approaches, so not deep neural networks. They have very good tutorials associated with them in a variety of locations, Coursera, DataCamp, and elsewhere. Even the documentation that comes with the package is really good. And download it and fit, some your own data or some sample data. Another good place to look is at a lot of the conferences, both regional and national conferences like PyCon for Python or SciPy. They will have like day-long tutorials, hands-on, sometimes with the people who write the packages, and you'll be able to spend a day or half a day with those folks. There are meetups around Nashville. Tonight I'm going to a PyNash meetup where they're going to talk about data science and making better beer with data science. So how could you pass that? And so we won't learn much technical stuff there, but in other meetings, they'll have tutorials on some of this stuff. So go to meetup.com for Nashville and look up some of these things, and you'll find places to learn.
I'll also mention a lot of students come in and take Coursera class by Andrew Ng called Machine Learning. It's probably the oldest such course out there online. It's been watched by probably 1 billion people by now. Fairly successful. It's another good place to start. I wholeheartedly agree. I would not start with deep learning for a host of reasons.
Mm-hmm. And just as maybe a practical note, when you actually kind of get started on your new machine learning project, you'll probably spend like half your time just wrestling with your data to get it into the right format, and like wrestling with the code, and like this version of this doesn't run with your version of this, and it's really a pain. All machine learning researchers do this, so like you're not, don't lose heart. We actually we've just gone through that whole process in our lab. My students are like nodding and laughing because yes.
That's right. If you're using anything for Python, there's Python 3.6 versus Python 2.7, and you're going to have all kinds of problems dealing with those too.
Yeah, I often get very clinically minded folks who come to who really know their space and think maybe they want to actually learn the data science to try to apply it, maybe machine learning. And so totally agree. The data pre-processing part is usually well more than half the time in the project. And I always say in my lab, it's much more about attitude than aptitude. Everybody in this room is smart enough to do it. It's much more like, can you sit there and fight the data to get it in the form that works? And then when you get it to work, you get that little dopamine tickle in the back of your head that keeps you going. Because when you get that, then you've got that feedback loop and you're going.
Yeah, you can even take a step further back from learning machine learning, and some of you may already be past this point, but you may be a graduate student or a scientist who is not a computer scientist or a statistician, and just doing, Python programming, and Git and GitHub that's kind of step zero.
Yep.
So we give a workshop once a year called Software Carpentry, where we learn the basics, how to use the Unix shell, how to do version control, how to deal with databases. And you'll find Software Carpentry and associated workshops around the world these days, and so you can look for those as well. There are places to learn those.
So I can share my experience to learn deep learning. So I think I learned deep learning about using one mouse to learn the deep learning. Before I learned that, my background is I know how to use Python. I know basic idea of machine learning, and I know neural network, but I have no idea what deep learning is. So the first step, I read a paper called Deep Learning in Nature, which is written by the 3 founding fathers of deep learning. So which basically just 4 pages without any equation, general introduction of what is deep learning, which is key component in deep learning, how the development of deep learning in the past several years. Then I downloaded PyTorch. At that time I downloaded TensorFlow and just run the basic examples it provides. Then I know how to read the data from hard drive to fit the deep network, how to choose the parameter, how to tune the parameter, and how you show the output, those kind of stuff. Then I go back to see the milestones of the deep learning, like from the VGG, ACCRE, VGG, ResNet, DenseNet, those kind of stuff. Each year it basically have one big breakthrough. So I figured out what the milestones are. Then I go on another direction to see different applications. What's the basic network for different applications? Then I see, okay, if you do the natural language processing, this is like RN, STM. If you're doing segmentation, it is like basically fully convolutional network. And if you do like other things, they're basically have typical standard network to do that. So on two directions, I basically get the big map of different. And you can focus on the particular area, like I focus on image analysis and the segmentation, so I just focus on the convolutional network, that part.
We have time for one more excellent question.
Forgive me, everybody. I got to run back to clinic. Thank you all very much for the attention. That wasn't a setup to get my applause.
Yeah. So there's two competing questions. So how about Nick? You can ask one, and maybe one person answer that, and then Jonathan, you can ask the other.
So we've already heard about what changed in the last 3 to 5 years to kind of jumpstart this. I'm kind of curious about the next 5 to 10 years. And right now we're still having to make a lot of choices to get machine learning started. What does the future hold?
What does it hold in terms of what, technologies or?
I guess technologies, but also in user applicability. So how close are we to just having a data set and a user gets to say the ideal, holy grail, go, and you get back an answer?
That's a good machine learning question.
Yeah, I think that for my prediction would, and I'm biased because of my background, but the merging of sort of statistics and machine learning, and so incorporating probabilistic concepts associated with this stuff. And you're already getting some of that. There's a prominent machine learner called Zubin Garamani, who has a project called the Automatic Statistician that makes reasoning about what to analyze from a particular data set. I don't know, I think that it's a bit of a siren call when you have automatic inference. I'm not sure you necessarily want a button to push. You always, I think, want a human involved in making choices about things. But I think there will be increased automation, but certainly merging more probability, incorporating uncertainty into predictions will be a bigger trend. I don't know if anybody else has a big one.
I'd add a couple of things that at least I see the trend. I think it's impossible to predict 5-year horizon, but at least in a more proximate future, there are 2 major things that people seem to be really interested in. One is causal modeling plus machine learning. So getting machine learning to be causal, very hard. Nobody really knows how to do it, but that there's been a fair bit of research and more to come. And the other one is explanations. So things like deep neural networks. How do you actually, or interpretability or explanations, how do you actually interpret the results that it gets? So those are the 2 things, I think.
Last question.
Okay, so I think a lot of us have seen these cool images that come out of Google's deep dreaming project, and it makes me think, okay, so it's sort of doable to train a system to recognize cats and say, find me a picture of a cat. But how close are we, or what would it take to get to the point where we could say, hey, draw me a picture, create a new picture of a cat?
We're there.
Yeah.
We're there.
Convolute, yeah. Variational autoencoders will do that for us already.
Awesome.
Yeah, also generative adversarial networks is created by this guy named Ian Goodfellow. He wrote a book called Deep Learning, if I remember correctly. So those are worth looking into as well.
Help me thank our panelists.